Um, my name is Carsten Schilde. I'm working at the Institute for Particle Technology at the Technical University in Braunschweig. I made my PhD in 2012. Working on grinding and dispersing since I started at the end of 2006, and then at a certain point I go deeper into numerical modeling, and yeah, since 4 years roughly, I'm also using these numerical modeling methods in combination with data-driven modeling. Some of you already have heard some talks of Christoph Thon, who is a PhD student of my group, and yeah, has often different talks about different AI modeling techniques we are using today. I focused more on a combination of numerical modeling with data-driven modeling with regard to grinding processes, and what we are doing, especially also on the numerical part. So I will show some slides regarding the data-driven modeling, and but more related to the last talks on the numerical stuff. Yeah, the work I will show in the next maybe 40 to 45 minutes is related on a joint work of a lot of PhD students, and they are supervised by me, also by Arno Quade, and combined supervision and whatever. So different works combined here for this talk, where I want to give it an overview on how we are thinking on how to model grinding processes and what are our basic thinking, and depending on this basic thinking, how we use then numerical and data-driven models. So to start with, hopefully you will see the next slide now. When we are talking about grinding processes, we take a look on different grinding processes, but our main working horse and our main focus is typically on steered media mills. I think I don't have to say a lot of things on steered media mills. As you all know, they are used in pharmaceutical industries and very small scales, starting from several 10 to 100 milliliters and going up to several tens of cubic meters, used in the mineral mining industry. And there are a lot of questions regarding the grinding process, depending on the material on the one hand, on the other hand, on the process parameters. And typically these mills are used in a grinding circuit or in a whole process chain. So flow sheet modeling or population balance modeling, how it behaves as a whole process in a process chain is also very important. And we have also some dynamics of these mills. So we have a steady state process operation window, but we also typically have certain dynamics because of viscosity effects, of variation in the feed material properties, the grinding media distribution, and we have start up and run down processes, and also we have this circuit operation together with other processes such like sieves, other mills and crushers, or flotation processes. So everything deals in our institute, or mostly with the steered media mills, and we have a certain approach to describe these mills. We try to separate during the modeling machine and the material, and a machine function and a material function, which is given here on this slide. On the upper part, we have our machine function, which depends on the geometry of the mill, the process parameters, the grinding media. And depending on these parameters, we end up with certain stress conditions. Is it more due to compression or due to shearing or impact? Typically in steered media mills, we are more related to compression between surfaces, between the grinding beads. And these grinding beads has in the mill a certain kind of stress energy distribution and a certain stress frequency, and this defines our machine model. On the other side, we have our product model, our material model, which could be limestone or a mineral, but could be also a yeast cell. And the yeast cell and limestone or other minerals have typically totally different material characteristics, which can be described, for example, by a breakage energy distribution or probability distribution, or a progeny distribution, or also a fatigue distribution. And the combination of these both functions lead then to an overall grinding model, and from this model we try to derive parameters which can be then used also to predict grinding processes. In our case, we often use population balance methods. That means we need an expression for the breakage rate, we need an expression for a breakage function, fatigue function, and then go further within our modeling. Just a very short overview. I think 90%, 95% of you all know how we are dealing with our models from the machine or product related model. We have the stress model according to Arno Quade, which is on the one hand defined by the type of stress, in our case compression between these grinding beads shown on the right side. We have a certain stress number. There are existing equations from PhD students and research work from the last 25, 30 years. For example, for grinding, it's shown here depending on the filling degree, on the grinding bead size, on the porosity of the grinding media bulk, and also on the number of revolutions, but also on the particle size, which can be seen here on the right side, on the D0 or X at a certain time in the grinding process. And at the end, apart from the stress frequency and the number of stress events, we have also the stress intensity, which correlates more or less to the kinetic energy of the grinding beads in the contact. That means it's based on the relative velocity of our grinding beads. And these are the basis for our machine-related model. And however, these basics depend on different parameters and different phenomena on different scales of our system. So just if we take a look, for example, on the aggregate or product particle side, we have a certain strength which depends on the structure of our material, on the properties of our materials. If we go then a scale larger, then we have the capture probability of our particles in between our grinding media, which depends, of course, again, on the structure, since the drag coefficient, for example, depends on the structure. And they are also changing the coefficient of restitution depending on their properties. So here on this level, we can mainly take a look on what's happening with the coefficient of restitution in our during the approaching or during the approachment of two grinding beads. Are the particles captured? How many particles are captured? What about the capture probability? What about the coefficient of restitution of these grinding beads? How much energy can be transferred to the product particles? And you can investigate this. I come to that point later a little bit. And you can increase your scale even more on the mill scale, where you're not able to simulate the product particles anymore, since you have billions and billions of particles. So you have to just take a look on the grinding media movement with a steered media mill, or here just to have an eye catcher, which is a shaking flask with fluid and grinding beads inside with a turbulent surface. And you can take a look on the relative velocity distribution within such a mill, and that means on the stress energy distribution in the mill. And you can differ between different stress mechanisms also. And this can be then used, hopefully, in order to get a machine model which can be used for population balance methods or for process optimization, process control. And this is just the part of the numerical simulation. The question is always why we are doing this simulation on the different scales and look into the different phenomena. Of course, some of the results and the values, for example, the relative velocity distribution in such a mill cannot be obtained via measurements, or is difficult to measure, needs a lot of expenses. And then we have an advantage here. That means the CFD, DM simulations, population balance method, they are good for simulating systems. However, they are still limited. And now here the AI stuff comes into play, machine learning algorithms. And it's similar to the things that are shown on the right side here on the slides. If we are thinking about molecular structures, for example, we have the simulation of protein structures, which has a certain evolution during the last years, but the structures are getting larger and larger. It was a little bit plotted in the last diagram here a few seconds before. And in the past, until 2019, they are able to simulate 150,000 molecular or protein structures. And afterwards, they started to use these simulations and structures to train AI machine learning methods, developing this AlphaFold method for protein structures. And afterwards, after this development in the last 2 years, we are coming up with 600 million protein structures, starting from this 150,000 structures in 2019. That's a huge impact on, or a huge progress and a very fast progress. And the idea is to transfer it also to other simulation methods, for example, such as the DEM, since the DEM is working on the same principle, the second law of Newton motion. So now thinking is to make similar things at the end and incorporate AI to have fast iterations to have less simulation effort needed and a similar number of simulation results, for example, and also to use this to have post-processing of our simulation to deal with the data, what's happening with the data afterwards. And if you think about AI methods and data-driven models, apart from numerical models, typically they are used for process prediction or prediction of a certain task. And as a basis of this prediction, you can then use process optimization. You can use these models, which are typically black box models, for process control. You can make fault detection. But since they have a black box character, you cannot transfer these methods to other process geometries, other feed materials, or other process scales. And that's a huge drawback. And that's the reason why we are thinking of how to use these models also to have a kind of hybrid modeling or to derive equations based on this data-driven approaches again, in order to make the scale up simpler again, which is then a step back to this classical engineering goals to have analytical equations, which makes it easier to have scale up. So we have certain issues and high demands also on the data and on the processing. Which is similar in experiment and also simulation. So you have to know what you do, and the goal at the end is to get to some methods which make a process control able, or to have the ability to derive physical equations again. So, and I would like to start again with these numerical methods and then try to show cases where AI could help to improve these numerical simulations and the post-processing of this. I would start with capture probability. What we have done here in the past, we set up this case of two grinding beads approaching with different velocities, different angles, and different rotation of the grinding beads. We put in between several product particles, and then we take a look how much particles will be captured, what's happening with the coefficient of restitution after the contact, and you can derive velocities for different starting velocities of the grinding beads. And then you use this, and here on the right side, you can see it a little bit and take a look what's happening with the coefficient of restitution, but you can also take a look on what about the capture probability if you have, for example, here as it's shown here in the table on the right, an increasing shear velocity, not only normal velocity, what's happening in shear direction or even rotational direction. And what you then obtain from the simulation is that you have a slightly increased 20–30% of capture probability if you have rotational velocity, additional to the normal velocity. That was an output which is just a rough estimation based on the less simulations we did. So we did a lot of simulations, but to quantify this output, it's hard to do. And afterwards, you have an impression on what's happening with the coefficient of restitution. You can calibrate lubrication models in between the grinding media, which are necessary to simulate, for example, such a mill. And you have also an idea how much particles are captured in between. And with this information, you can go into a larger scale simulation of the whole mill, which is plotted here, which is done by the simulation software Rocky, where we have the fluid phase represented by a computational fluid approach and the discrete element. We have a coupling in between. Since we have a lot of particles, we need a four-way coupling, that the particles influencing the fluid phase and the fluid phase the particles and vice versa. And what you can derive from these simulations are such stress energy distributions depending on different grinding media sizes and grinding media materials, different tip speeds, and you can derive certain models. And if you do so and take a look on these results, you come to the conclusion that the model of Arno Quade works quite well. There are slightly differences depending on the fluid, on the viscosity of the fluid. But overall, if you combine, especially the stress energy and the stress frequency, it works very fine. However, what is the additional thing that you can get from this simulation is that you get the stress energy distribution for different mill types and different mill scales and different grinding media materials. And this is something which is not implemented in the traditional grinding model up to now so far. So there are some extensions. And what you can do also is you can also take a look on not only the normal stress energy, you can also take a look on what about torsion stress energies, what about shear stress energies, rolling, or combined versions, which looks a little bit weird. I just put it in here in the slides, but we will not discuss these results. But you can extract a lot of information from these plots, what's happening inside your mill, what's happening on the rotor, what's happening to the wall in between the particles. And the question is now, how can we use for different machine learning approaches here to take further advantage out of these simulations? The issue is that these simulations nowadays for the whole mill need a lot of time. So you need several days for each simulation. And if you have different mills, different setups, different process parameters, this needs a lot of time. And you can use traditional artificial neural networks, which are plotted here on the slides. I think everyone knows in principle, we have input layers, we have hidden layers, and we have output layers, and we have weights in between the nodes. And the weights will be summed up, which will be shown in the middle of this slide. And if they are above a certain threshold, then we have an activation function. This activation function gives us a new weight for the next hidden layer. And we have sparse distributed systems. We have full connected artificial neural networks. We have different combinations of input and output layers. We have different variations within these neural networks, which helps us to model our process. There are, of course, other methods which can be used and are helpful for modeling. For example, we use very often genetic algorithms and genetic programming. Also, symbolic programming is actually implemented in our working group. Or what's happening here, it's all about evolution. We are starting with a certain population which has some advantageously properties regarding our issue and some negative properties. And then we select the best ones out of them. We make a kind of crossover, as it will be done in during evolution. We make point mutations, for example. And afterwards, we take a look on our childhood or our daughter population, and then extract again the best individuals having again selection, crossover, mutation, and so we have a kind of a wheel or a circle which will improve over a certain number of epochs. And if we want to apply this both methods, I will first show the neural networks to our simulations. We can start with, for example, our CFD-DM simulation of the steered media mill, and we can divide our mill in several slices, and every slice in a certain number of voxels, which is given here in the next slide. How it works on the left side, I think some of you have already known this approach. So we divide our grinding chamber in around 40,000 voxels. And for each voxel, or for this system, we train an artificial neural network, which gives us the relative velocity for each voxel, or the stress and energy distribution, the stress energy for each voxel. We can sum it up for the whole mill and then have a three-dimensional stress energy distribution for the whole mill. We can do this for 20 simulations as basis for the training of the machine learning system. And then the machine learning system hopefully is, here it's how it works, is then able to transferred to other process parameters. Here, firstly, it's shown that it works in principle. So here are the predicted AI values of the artificial neural network compared to the simulation, which is in a good agreement. But if you do some extensions of your modeling, you can come to even better ones. I will show it in the next slides. But this is the basis. You can take a look what's happening with the relative velocities, for example, at the different slides from different parts of the structure, the rings, or on the right side, what's happening with the relative velocities between the grinding beats within the holes, for example. And yeah, the agreement is quite good. And based on this 20 simulations, we can then predict 10,000 theoretical process parameters, which 1,000 or several hundred, which means you don't need to simulate them anymore. It's just like a kind of intelligent interpolation in between the three-dimensional stress energy distributions. That's the core what the machine learning system here is doing. Nothing else, but it saves a lot of simulation time. And the more generalizing your system is, the more effective it is. The question is what to do afterwards, what to do now, and how to deal with this stress energy distributions we obtain from our simulations and predictions from our AI model. And this is a part which can be implemented in the bracket rate term, for example, if we do population balance systems. As you remember from the start of this talk, we have the process model, which is here depicted in blue, and we have our material model in red. And the machine model is based on the stress energy distribution, on, of course, also on other parameters, but we can try to describe our bracket rate of our population balance system using this kind of stress energy distribution. On the other hand, we have our material property we have to measure, or we have to calibrate depending on the material properties. We developed a two-roller tester in the last year. Malcolm also did. And then based on this two-roller tester or other testing devices, we can have an impression what's happening with the bracket function, and these are the two factors or the two things we put in our population balance model. And from the DM part, of course, we can, the slide is a little bit weird here, but we can, hopefully the next not, we can do two approaches. We can try to use the model from Arno Quade, which gives you characteristic numbers and which is true for 1 mil. Or we can try to use the CFD-DM simulations, and the combination with AI gives us the stress energy distributions, which are given here on the right side for different process parameters, and based on the stress energy distributions, we can try to get our breakage rate. And this is something I will focus on in the next slide. So I will start before starting with it. I introduce also the material function. In our case, we measured our bracket strength also with the nano indentation device. In this case, we don't use the two-roller mill in order to derive the bracket function. So we calibrate, or we fit the bracket function. So it's not the perfect way to go for, but that was our approach at this time here from the results I will show in the following. And then I will just show you how we are thinking about to put our stress energy distributions from the simulation in the bracket rate model for the population balance model. And for that, we use, of course, the stress energy distribution, but we need also the strength energy distribution, or the bracket probability distribution of our materials, since we have to compare both of them. And here we measure them with the nano indentation device. So we compress them, take a look, when a single cell or a single particle breaks, and then at the end we get such bracket energy distributions on the left side for yeast cells, on the right side for limestone at different particle sizes. And now we are using both the stress energy distribution coming from the mill and the bracket energy distribution from our material, and try to combine it. This, which looks a little bit complicated, but it's not very complicated. So here on this plot, we just change the direction of low to high stress energies here, and having just a part of our stress energy distribution we derive from our mill simulations, which are here depicted in the red line. So we have 3 different lines at different tip speeds within our steered media mill, where we derive our stress energy distribution. And these are parts of the stress energy distributions. And we have in blue the bracket energy distribution of our material. And now we try to weight every single bracket energy of our material with the number of stress events in the mills that has higher energies, and sum them up, which is given here by this expression within this integral. So within this integral, we just sum up for each bracket energy all stress events in the mill which are larger, and then sum everything together up. So we weight these 2 functions to each other, and then get a kind of an effective collision frequency. And this effective collision frequency we then plotted as function of our bracket rate we obtain from experiments, which is given here on the x-axis, which is this complicated term of this effective stress energy distribution. On the y-axis, we have here the burst rate of our yeast cells, which works well, since yeast cells have just this on-off. They are bursting, they are intact or were burst, and they have low stress energies. For both cultivation conditions of these yeast cells and both strength or bracket energy distributions, we get a straight line. That means good, where the results are in a very good agreement, since there's of course an offset in between, but that was what we expect. If we go for limestone, we have also a certain kind of a line of a linear dependency, but we have also some outliers for different particle sizes. But in principle, it seems to work. However, if I stay at 1 mil, we can also thinking about using the model of Arno Quadre, which works also. But for different mills, different setups, different variations in the feed material, this is a good way to go for. And we put this bracket model now in our population balance, which is given here. This is how our population balance model for grinding processes work. So we have our parameter implementation, we have input settings, then we run into our steered media mill population balance model script, which is subdivided into different cells. So we do the population balance method for every cell within the grinding chamber. So the grinding chamber will be divided into different cells, and we connected these cells, and for each cell we run into a loop and performing, for example, the grinding model with the breakage rate and also the breakage function at the end, so the source and sink terms, the birth and the death terms for our population balance method. And we have certain other models. So here, this part here on the right side is our grinding model, but we also need a power model. We need a product transport model through our mill. We have also a rheology model, which is currently empty here, as you see. We have a grinding media distribution model, which is also here in this state of our population balance modeling empty. And with this, then, if we calibrate the breakage function well, we can predict how the density particle size distribution changes. For example, if we change our volume flow through the mill, which is here given on the left side, or if, for example, the solid concentrations in our inflow changes, what happens with the particle size distribution within or at the end of our mill during the time. So, however, apart from it, that's just how we were thinking on using and combining numerical modeling in the past. And now we can think about what's the future and how to deal with it, and how to bring AI models more into play, especially, for example, for process optimization, how to get it, or for how to derive models for process control, and or to be higher flexible or to reduce the cost using AI models. And one thing that could be done, not easily, but is part of a project in our institute, is to use this population balance model here on the left side. This is I've shown before, and put it in a nonlinear model predictive control, and which is just the workflow, how it works at the end. You put in the population balance model, you make predictions of the particle size distributions in the future for different settings, and depending on how the difference between the goal or the target values, product values are, and the actual values, you get different process control. This is this traditional nonlinear model predictive control, which comes up in the last years. We are still working on that. I cannot show results up to now. But this is one thing to do, and to control how the whole particle size distribution evolves. And another thing could be, which also Christoph Tone shows last week in Cape Town, as I remember it right, you cannot also not use a population balance model, but you can describe your process using machine learning approaches. And if you do so, you can do similar things. I would call it then model predictive control. And you also use your machine learning, your artificial neural network, to predict several states, process states at different process conditions at different time steps in the future, and then choose the best one to control your process to reach your target value in the best and fast manner, and also in a robust manner. That's the other thing that can be done. But with this, I want to switch over to other possibilities we have nowadays. And if we think back on the simulation of our steered media mill, on the stress energy distribution within our mill, we can think about using AI methods to continuously change our morphology during simulation. So we have our rotor geometry of the steered media mill, and during simulation, we are trying to evolve these geometry, the disk with the holes, towards one which has the same energy input, or the same power, the minimum specific energy, or the specific aware of our rotor system. And how we implement it is given here, the whole principle in this colored bubbles. So we have our simulation. Then based on this simulation, we made a point cloud out of our geometry. And this geometry will be then similar to what a genetic algorithm is doing, mutated. We have crossover of different geometries coming to a new one where we expect is, for example, a reduced wear in our system. Then based on this point cloud and the mutations, we again create our CAD model and go back to the simulations. And at certain points, every time when the simulation has a steady state, for example, of the energy input, then we go back to this genetic algorithm and change our geometry. So we have a loop during the simulation. The whole workflow is given here. How it works, but in principle, I described it just before. And we started this, Christoph Thon implemented it with a few master students, and the methods work well. But however, we choose informatics student, which has not any idea how steered media mills are working and how grinding processes are working and what's happening inside. So he don't realize that our rotor within our steered media mill is point symmetric. And he assumed that he is plane symmetric. He put in the plane just in the middle, and then he let this system evolve in geometry during simulation. And then we come to this Halloween masks at the end, or they are looking like Halloween masks. And there are also some issues, so you cannot produce these things at the end. They are not point symmetric. So there's still a lot of work to do. But it gives us, or gives you a first idea of what will be possible in future. And you can go also to dry grinding processes. Here we use convolutional neural net to describe also the whole stress energy distribution, the whole mill. We make some adaptations. We put also a genetic algorithm here in the machine learning of this after the simulation. So we simulate again 15 simulations of the mill. Then we divide it into different voxels, 30,000 voxels, and then we train a machine learning model. And in order to get a better model out of it, we put in this genetic algorithm also within the training of our artificial neural network, and then the results were much better, much better comparison, or much better results of our prediction compared to our simulation. So here we have the velocity distribution within this mill, a bimodal distribution. And if we want to search for differences between the three-dimensional velocity prediction and the simulated values, they are quite small. They are here in this area. There are some differences, but this shows the potential what's happening. And if we are talking about dry grinding, we then have to think about what's happening about the probability of particles captured in between particles, since we then not talking about single particles anymore, we are talking about bulk material, which will be captured. And this bulk material captured between the grinding beads depends strongly on the flowability of the powder. And that's the reason why grinding processes having different grinding acids, given here on the slides, top left, have different grinding results depending on the flowability, even at similar operating parameters. And normally the DEM simulation will give you the same results. The question is, what's happening with the stressed bulk in between the particles and how the energy is distributed to these particles. You can make different experiments to characterize, for example, you can have this fall weight tester and having product material in between the grinding bead and the surface, and take a look how much particles are captured depending on the material properties, the flow properties, which will be given here in the next slide. I will try to hurry up a little bit to finish in the next few minutes. This is given here from the experimental point on the left side, and then you can use these results again to train an artificial neural network. And if you do so, you will mention that you need more data than just the process parameter of the experiment. You need the flow properties of your product, the ring shear data. That means the flow function, you need the cohesion, the effective friction within your bulk. And if you put this information also into the training of an artificial neural network, predicting, for example, the flake weight and the resulting restitution coefficient, you come to quite good results, which will be given here in the top right, where you have different process parameters. Here, just on the x-axis are different experiments, the number of different experiments, and on the y-axis, how the predicted values and the measured values match each other. So there are certain ways to put in artificial neural networks also into calibration of grinding parameters. Here, another example is given by the two-roller tester, which I will not go into detail. But the question is, here you have a black box model, and would be favorable to get out an equation for the capture probability or the captured mass depending on the flow properties and the experimental parameters. And in order to do so, you have to think about, can I use the data out of our artificial neural network to get a physical inspired model again? That's the goal. And here we use genetic programming. I just showed how it works in principle, which is here depicted on the right side. We have our data, and based on this data, we train we use genetic programming to create these tree structures. And these tree structures gives us the formula where the parameters are at the end and the mathematical operations are the nodes of the tree. And the genetic programming is exchanging parts of these trees and mutate parts of these trees, finding the best solution for an equation. However, this equation is then empirical. And in order to put in then physics, you can think about this part here on the top left to make a kind of dimensionless analysis and put it inside. So you have dimensionless numbers. You can check if they are part of the solution of your equation. And you can also put in physical knowledge from literature or from your DEM simulations. You can put in the contact forces or the model of Arno Quade or whatever in a library, and check then via this artificial neural network if this part, this dimensionless number of this physical equations or parts of them are part of our solution. And this brings us physics into our equation derive. So we tested it also. I will jump over it, and it works fine for the most equations we get from literature. But the workflow is as following. We have a kind of a simulation, which is not a grinding process here. I'm sorry for that. Then we are doing a kind of black box modeling in order to have virtual data as well as simulated data or experimental data. And then we are using this genetic programming in order to derive here, the black line, a certain model which is hopefully physical inspired. And since I have no example for the grinding process up to now, I will show it on the simulation of the drying of a lithium-ion battery electrode, where we predict the height of our system using this genetic programming, which is given here in the middle. So we derive the function of the height of the electrode, of the porosity of the electrode, based on the particle size distribution, based on the areal loading, mass loading, or the initial wet coating. thickness. So there are other possibilities. They are more enhanced for example, deriving surrogate models in future. So be faster with the DEM simulations, which I will not explain now. I will now jump to the conclusion, what I have shown today, in order to have some space for questions afterwards. I show how our thinking is of modeling grinding processes for numerical as well as artificial or data-driven modeling, how these methods can give us information or leads to kind of post-reduction, acceleration of simulations, and how to deal with the output, how to optimize geometries or process parameters, and how AI could be a multiplier. There are a lot of other opportunities in the future, and with this I will have a lot of thanks to my research team, which works on these topics, and I will thank you for your attention.
Thank you very much, Carsten. Very interesting presentation, and now we have time for questions. Anyone here? I think Johannes.
Hello, Carsten. Thank you very much for an interesting presentation. My name is Johannes, and I work at the Fraunhofer Chalmers Center in Gothenburg, Sweden. So, very interesting talk. I have first a detailed maybe question. So, how do you define the normal stress energy for each particle interaction in your DMCFT setup? You're muted, sorry.
So the normal stress energy is quite easy. You have the relative velocity, you have the mass of the relative velocity during the contact, just when the contact happens, which may be damped due to the fluid before. So if you have a lubrication model, of course, the velocity is damped, but if you have a contact, you're using this relative velocity times the mass, velocity to the power of 2, and times the mass of the grinding media. And then we are using an ideal plastic contact. That means 1 to divide it by 4 in front. It's a simple one to do it, and it don't take the deformation of the grinding media into account, of course, the energy which will be dissipated within the contact. But the main question is how much energy will be dissipated within the deformation of grinding media, since we have product particles in between, which have often a lower Young's models, for example, or they have a certain strength. And so there's a lot of energy dissipated into the particles. So it's difficult to handle this. But in principle, that's it. Not a complicated one.
So what's the relationship between the simulated particle size and the actual bead size?
You mean,
do you simulate the actual bead size, or do you do a coarse graining for the beads?
For the beads, we are using typically the actual size. If we be in the range of 1 millimeter, 2 millimeters, 3 millimeters. But if we are going to low, so our mills are not as big as your ones, maybe. So we have 1 liter mills, for example. So then it's easier. If you're thinking about getting smaller particles, then you have to think about coarse graining. Our approach, or the idea of Christoph Thorn, I think he is also within this call here, is to simulate it for the large grinding medium, try to predict it for the smaller ones. But in order to have a good prediction, via, for example, machine learning approaches again, he then cut out 1 slice out of the mill to reduce the number of particles in simulation, just simulating 1 slice on the larger mill, as well as on the smaller, with the smaller grinding beads, the same mill, but the larger grinding beads and the smaller, in order to make this prediction a little bit more reliable. Not to predict within a black hole, also have a kind of simulation on the small scale, but only a small slice out of the mill. Maybe a disk with a certain surrounding if you think about the cell models of steered media mills, that's the idea here from Christoph at the moment. Hopefully it works well, but the larger the mill, the more challenging it is. There's another solution that I have not shown here, the surrogate modeling. You can maybe simulate a certain cell size with particles inside, and for all conditions which are possible, and then train a machine learning on the particle movement, the new positions, the forces, the velocities, and then transfer your simulation of a very large mill into a mesh-based system. And instead of solving, for example, Navier-Stokes equations, you are solving this machine learning. However, if you do so, you have to put in the time into your training. You have to train in tesseract instead of a volume, since otherwise you get an accumulating error, since your machine learning model is never be exactly the simulation. So in order to avoid this accumulating error, that are possibilities we are working on, but I have no solution.
Okay, interesting. I have one more question, but I will leave the floor to others also to ask.
So I think we have a question from Professor Marcelo.
Yes, hello, Carsten. Fantastic seminar there, but apologies, I could only get half of it because I was stuck in traffic here, too early in Rio, but the part that I got was really impressive. And yes, I've been following closely your group, and indeed, I think you're taking very nice steps into dealing with the complexity, because I think you nailed, in my opinion, one important issue here, which is really to predict the milling performance. You really have to get a good estimate of the material capture. And yes, since Paul's work that I see that you're more or less pursuing that, correct, as with getting more data to understand how much material is captured as a function of fluidity and everything. I believe that's the way forward, to understand more of the physics, to be able to couple with all those techniques and population balances. So it's good to hear that you are pursuing this path. We are as well here, because my comment is that, yes, in the core size range, we have been very successful, I'd say, when we deal with very large grinding media, like 25 millimeters, 30, 50 millimeter balls with millimeters, sub-millimeter size particles. Assuming that you have most of the time down to a monolayer stressing condition, using more or less division from Carl Schonert stressing volume. But indeed, I think the question when it goes down during wet milling is exactly how much of that material is still being able to be nipped by the grinding media. So yes, I believe there has to be a coupling of more physically meaningful models, and also somehow some back-calculated information or AI type of empirical models to be able to fill the gaps as you go to really find sizes. So it's just a comment that it's good to see that you're pursuing that, because in my opinion, that's exactly the missing link. Because the EM-CFD, you can definitely do very nice simulations, but that basically you have very few degrees of freedom when you want to be able to describe your system. And then it actually population balance, that's where our approaches differ a little bit. Ours has a few aspects that you guys don't use, but still the differences are not huge. I surely believe in this mass capture is one important area. So great work.
Thanks a lot. So there's still a lot of work to do. Regarding the population balance model, we are often, and had not talked about it, we are often using your wreckage model since after my last visit in Rio.
Oh, good to hear.
So, several times we are using it. Yeah.
That's what I meant. Like, what's in that report? Like that.
Are there other questions?
So then I have one more question. So I was thinking about your nice method there to use the neural network to represent the, let's say, the cells or the or so of the mill. Have you also tried to compare the genetic algorithm as a to me, it looked like a model structure of the AI system to be able to perform like optimization. Have you compared the accuracy of the genetic algorithm model to the DEM CFD data? And have you tried to compare that to the DEM to AI to GA?
It's now related to this morphing surface, or it is more related to this idea here for having a surrogate modeling replacing the DEM by a machine learning approach?
Well, I was thinking about in the beginning, maybe slides 17, 18 or so, you showed how you used the AI, yeah, basically to represent what happens in the mill. And then I think you show that from this, you then fit the genetic algorithm model to this.
What we have done afterwards, we input. It's something we are just working on to make then the process control out of it.
Yeah, because I mean, now you're doing DM, AI, GA, right?
Yeah.
Yeah, I was just thinking if you then you could train or verify by checking GA back to DEM to see how well it behaves, let's say.
Yeah, we didn't do it up to now, but there are a lot of things missing in the process chain. I've shown.
Yeah,
here.
it was just an idea.
It's there are a lot of things which should be done. Also, some improvements, some validations on different parts of the whole thinking, which has
yeah, it was
to be
not
done.
a critique. I was just
No. You're right. You're right, and you have to think of and also that's the issue is now we have the stress energy distribution here for the three-dimensional mill. Which cannot be used directly for process control. So you have to do something in between to use it for process control. And sometimes it's easier to have a process running and you just take a look on the experimental data to make the process control using machine learning. It's much easier than try to use this one. At the moment, we have this project to put it in the population balance and then have the nonlinear model predictive control. And this is a direct correlation of the stress energy distribution with the process control. But for this machine learning process control, we didn't get up to now to get from the stress energy distribution to the process control we try to do it more on the experimental way at the moment.
Thanks. I think it's a very inspiring concept using this voxel-based and then using the machine learning framework on that. And I think that's something we'll try to bring in into our idea space of the machines that we are working on as well. Thanks.
So thank you very much, Carsten. I think it was a fantastic presentation. We are a little bit over time. So thank you again, and it was very nice. So
yeah.
Congratulations on the presentation.
Thanks to everyone here. And have a nice day, nice weekend.
Thanks, Carsten. Fantastic work.
Thank you.
Thank you.